Hi, Sagar. So I have a iPad and I've also joined in through the laptop. So initially I will need the spotlight on the laptop rather than on the iPad.
Okay.
Thank you. So I guess it's 11:30. Should we get started, Sagar?
Yes, sir.
Okay. Thank you so much. Let me know if you've started the broadcasting.
It started.
Okay. Thank you so much. Hello, everyone. My name is Surhud More. I'm a faculty at IUCAA here. I work on both theoretical and observational aspects of cosmology. And so today we'll begin this brief introduction to cosmology that it's a series of 4 lectures that I'm supposed to give. Um, Cosmology is a vast subject, okay, and it's one of the very interesting kind of subjects. If you'd like to know a number of fundamental questions that have bothered mankind since ages now, right? So I'm. It's my pleasure to do this. Let's get started. So there's one quick thing about the questions and so on. So you can type the questions to me in the chat box. I will be trying to monitor it throughout. And once in a while, if questions pop up which are totally relevant for understanding some of these slides, then I will take them during the lectures. If not, then maybe somewhere in the middle of the lecture and towards the end of the lectures. I'm hoping that I will not go over time. I'll try to finish a little bit earlier so that there is plenty of time for questions and answers. Okay. So let's get started then. Okay, so I just wanted to begin exactly with these big questions, right? That I've been alluding to, that cosmology tries to address, right? So since ages, right, mankind has been trying to look at the heavens and then try to understand answers or try to seek answers to many of these questions. So we would like to know, for example, how old is mankind, right? I would like to know what are we made up of. How did we come into existence, right? We would also know what is the fate of mankind, what is our role in this big universe, vast universe that we see, right? So these are age-old questions, and unfortunately, they have been in the domain of religion for quite some time, right? Of course, as time has progressed and as science has progressed, we have learned that actually we can shift the focus, the human focus of some of these questions, to make that focus even bigger, right, and even better. And so nowadays, the bigger questions that you would like to know the answers to will be how old is the universe instead of just focusing on mankind, right? We would like to know what the universe is made up of rather than just to know what we are made up of, right? We would also like to know how did the universe itself came into existence? How did it progress from these initial nascent stages to whatever we see today, right? So that is another big question that we would like to understand. And of course, finally, everyone likes astrologers, likes to know what is going to happen in the future, right? So we would also like to know what is the fate of the universe, right? What is it that will happen at the end? Or is there any end? Or in the future, what's going to happen, right? So all of these questions now can be addressed scientifically. And that's the great progress that has been possible in the field of cosmology. So all these questions, which used to focus on the mankind initially, but remain kind of the basis of these big questions that you see today, right? These can be addressed scientifically, and throughout this series of lectures, we'll try to identify a few of these questions and try to answer some of these. Okay, so that's the goal of this lecture course or lecture series. Okay, so you have had plenty of lectures on initial astronomy that was done, for example, by our director Shomakrai Chaudhary, right, in the introduction to A&A lecture series. So I just wanted to give you a glimpse of it in the first few slides to set up the stage for cosmology. Right? So initially, when human beings started to observe the universe, of course, they didn't have access to telescopes or anything, so it was all naked eye astronomy. You see the sun, you of course see the Earth here, being on the Earth, but then you see the moon in the sky, right? And if you pay very, very close attention, then you can also find these objects called planets, right, which are like wandering stars. So stars which don't remain, or objects which look like stars, but they don't remain fixed at their positions with respect to the other background stars, right? So that's why those were called wandering stars or planets in Greek, right? And so these planets were the ones which could be seen. And so initial focus of cosmology astronomy was to try to understand the motions, how these planets move about, what exactly is going on, right? So the solar system itself, right? If you consider the scales on which the solar system exists, then the light travel time within the solar system is of the order of a few hours to a day, right? So this is something which was accessible with naked eyes, right? But as we made more and more progress, of course, we started to understand a little bit more. We started to put into context everything. Right? Initially, we thought the Earth is at the center of the whole universe and everything just revolves around it. That was, of course, one of the naive views, right? As you must have heard in the introductory lectures. Then we said, well, maybe the sun is at the center, right? And so we started to understand, to map out the surroundings around the sun. And so if you progress from light travel times of a day or so, then you go to light travel times of years. Right? Then this is the picture of the solar neighborhood that you get, right? So the sun is at the center, and then there are multiple other stars, right? You can see Proxima Centauri, which is the closest star to us, apart from the sun, of course. So that's about 4 light years away or so. Right? And then there's Alpha Centauri. There are other multiple stars that you see that have been mapped out in the solar neighborhood, right? So the light travel time is of the order of 10 years or so, right? In this particular. And so, of course, initially we would think that the sun is at the center, but that's just our vantage point, right? Because that's where we are as observers, right? So that is the picture that you get. But there's nothing special that you see about the sun. There are multiple other stars which look like the sun, right? There are some stars which are bigger than the sun, some stars which are smaller than the sun. So there is nothing special that comes out, right? Then you say, okay, let's go out a little bit even further out in scales, right? So then you're talking about galactic scales. Here, the light travel times are of the order of tens of thousands of years, right? And so then you look at the sun in the context of the other stars, and you see that the sun is not even at the center of our galaxy. Right? What you see is that the sun is somewhere in the outskirts of the galaxy. It's not like downtown galaxy, but it's in the suburbs of the galaxy, right? And you see again plenty of other stars which are just similar to us. There's nothing special about our position, about our location within the Milky Way itself, right? And so this is when you start to expand our knowledge or expand our view to distant scales which are of the order of tens of thousands of years. then you say, okay, this is just our galaxy. Can we look even further beyond, right? And of course you can do that. So instead of going from the solar neighborhood to the galaxy, now you're looking at the galactic neighborhood, right? So this is the Milky Way galaxy that you see here. And the light travel time of this picture is about millions of years, right? And what you see is that, okay, there are multiple other galaxies. So there's Milky Way galaxy, a neighboring galaxy to us, which is roughly of the same size, roughly of the same mass, is the Andromeda galaxy. So that, again, you can see right in our neighborhood. There's nothing special about our own galaxy either, right? And then there are plenty of smaller galaxies which are going around in this local group that we have, right? So again, this idea that maybe somehow we are special, that kept on getting blows after blows after blows, right? As we continue to expand our horizons and to look further and further and further away, right? So the farthest that we have, so some of the farther distances that we have explored is not just the local galactic group, but now to going to not just millions of years, but 10 to the 9 years or so, right? So it's going to much further away length scales. And there, what you can see is what I'm going to show you in this particular animation that was put forth by one of my friends, Mark Subarow, with the help of data from the Sloan Digital Sky Survey. So what you're seeing is we are just now diving into this 3D map of the universe that has been made with one of the galaxy surveys called the Sloan Digital Sky Survey. And now you can see that it's not just one neighboring galaxy which is similar to our Milky Way galaxies. There are many, many galaxies which are out there in the universe. They're just distributed like dirt everywhere, right? And each of these galaxies, some of them will be small, some of them will be large. Typically, they are of the size of the Milky Way, okay? So we are, again, nothing special. Sometimes you see that there are vast empty spaces in the universe, but then sometimes you see that there are conglomerations of galaxies which forms, like these galaxy groups, sorry. Let's go back. Like these galaxy groups that you see sometimes, right? So let me see if I can pause this once in a while when a galaxy group comes by, right? And so this universe is really vast. So this you can see like a tiny group here. But then once in a while, you'll see like these clusters of galaxies which are coming together in a very, very narrow region, right? So by showing you all of this, what I wanted to show you is by now we have understood better than to say that we are at the center of the universe, right? So you can see here a cluster of galaxies, for example, right? Yeah, so we have learned to understand that we are not really at the center of the universe. Nothing is special about our own galaxy. There's nothing special even about our own star. There's nothing special that there is this planet, except the fact that we are the only known living beings in the universe so far. Doesn't mean that there is nothing out there. It needs to be explored. It's just very, very difficult. It took us quite a lot of development in technology in order to explore all of these scales that you see. Okay. So what we want to do in cosmology is we would like to understand the universe at large, right? We would like to understand all these galaxies, how they come about. Can I describe the universe with a certain parameters, with the theories that I know? I know you have been listening to lectures on general relativity, right? So that is also the theory of gravity, the best theory of gravity that we have so far, right? So we would like to understand this whole universe in the context of the general theory of relativity. Okay. So before we move on to the general theory of relativity and how to put everything into context, let us discuss something called this cosmological principle, which was encapsulated in the previous few slides. Right? So I said that our place in the universe is not special, and neither is any direction. Right? So whichever direction you see lots and lots of galaxies, and this we want to codify as a principle. Right? So the principle that I'm going to talk about, there are these two principles, which on the first look of it, it seems like they are the same, but in fact they are not. Okay. So the two principles which constitute this cosmological principle is that the universe is homogeneous. Okay. So what do I mean by homogeneity? What I mean is that the universe is invariant under translations. Okay. The second principle is isotropy, that the universe is invariant under rotations. So if you look at one direction corresponding to or the other direction or the third direction, there's no difference whatsoever. Okay, so this is called the cosmological principle, right? And we want to study this cosmological principle in the context of general relativity and see what it gives us. Okay. The next important thing is to understand that the universe does change with time, though, right? So you have heard Shomak's introductory lectures in which he told you that if you look at galaxies which are further and further apart, they seem to be moving further and further away from you. We have also mapped out many of these galaxies, the properties of these galaxies, and we see that the further away we look, the properties of these galaxies also change as a function of the distance that you are looking at, right? And so because of the finite travel time of light, we know that the universe must be changing with time, right? So even though our location is not special, neither is any direction, but if you go out radially away from us, right, you see that the universe at different times, right, and you see that there is a particular sense in which the universe changes, right, and so what we are going to build models for cosmology are based on these principles, right, or based on these broad observations that we have, that the universe is homogeneous and isotropic, but that it does change with time. Right. So before we go to what kind of metrics can describe the universe, what I wanted to show you is how these principles of homogeneity and isotropy, how they are different, right? In principle, you would think that they are the same, but in fact, they are not the same, right? So it is very hard to imagine three-dimensional spaces. So let us think about two-dimensional spaces, okay? So what I want you to think about is the surface of a cylinder, okay? And assume that the cylinder is infinitely long in one direction. So in this direction, suppose it is infinitely long, and then it is curved in another direction. And so what I want you to consider is the surface of this cylinder, right? So if you look at the surface of this cylinder, whichever point on this surface you are, there is no difference whatsoever, right? You cannot distinguish one point on the surface of the cylinder from the other point on the surface of the cylinder, right? So this means that the surface of the cylinder is a homogeneous two-dimensional surface, right? But is it isotropic? Not really, right? Because one direction is special. Along this direction, for example, it's infinitely long. If you walk along the other direction, say along the curved surface, then you will see that you will come back to the same location, right? And so the surface of the cylinder, even though it is a homogeneous surface, it is not isotropic, right? So homogeneity doesn't necessarily imply isotropy. Okay, so these are distinct assumptions. What about the other way around, right? What if space is isotropic? Can you assume that it is homogeneous, right? So again, let's consider this two-dimensional surface. You are sitting on top of this cone here, and I want you to imagine the surface of this cone, right? So think about yourself as a two-dimensional creature who is sitting on top of this cone, right? You will see that each of these directions are exactly the same as you look towards it, right? But if you are at this location on the surface of the sphere, or this location on the surface, or on top of the sphere, there is a difference, right? And so this is an example of a surface which is isotropic from this point, but it's not homogeneous. Okay. So there is another theorem, which is if you have a space which is isotropic from two different vantage points, then it has to be homogeneous. Okay, so you can think about this, why this has to be true, etc. Okay, but that's the case, right? But what I wanted to show you is isotropy from one point does not imply homogeneity, and homogeneity doesn't imply isotropy necessarily, right? So these are distinct assumptions that we have to, right? And these are based on facts, right? So we have tried to observationally verify, and as far as we see, this is what comes out, okay? So now let's look at what is the form of the space-time metric that we can assign given these assumptions that we have made, right? So the naive thing that I talked about in the previous slide, right, that the universe is homogeneous and isotropic, but it does change with time. What you can do is you can express it as the fact that space-time can be foliated into space-like slices, which are homogeneous and isotropic. So there is a time direction. So you can basically think about space-time as R cross sigma, where R tells you what is the time axis, and then sigma, which is like a homogeneous and isotropic three-dimensional space. Okay? So the metric for the universe, the way you can write it down, it looks something like this, given the assumptions that we have made. ds square is equal to minus c square dt square plus some function of time multiplied by a line element which is defined on three-dimensional space. And that three-dimensional space has to be homogeneous and isotropic. Right? So observers that stay at constant space coordinates, okay, where the dl values between them don't change, right? These are called fundamental observers. Their coordinates are called comoving coordinates. So let me explain what I mean by that. But what you're putting in front of this dl square, so in front of this homogeneous space, you cannot rule out that there is some kind of scale factor which goes in front of this metric, the three-dimensional metric, which scales everything. Okay? We don't know what the functional form is. And remember, we have not applied any general relativity so far. We are just trying to figure out what is the space-time metric for the universe under the assumption of homogeneity and isotropy. This is what it looks like. Okay? So let me show you what I mean by that, right? So what I mean by that are that you can define some fundamental observers in the universe which are lying on this grid of coordinates, right? And they are not moving with respect to these coordinates at all. Okay, and what is happening as a function of time is that the physical distance between them is changing, and is changing because the scale factor in the universe is changing. Okay, so it was a of t1 at this point, then it became a of t2. So all these points, they just expanded out. All the distances in between these points, it just expanded out. Okay, and the ratio of these distances is just given by a of t2 divided by a of t1. Okay, that's all, right? So the same thing happens at a of t3, a of t4. This is what is shown on the time axis here. Okay. So the physical distance between any two of these points is given by a of t times the comoving distance. Okay, so there is one particular time snapshot which you can choose where you can define that a of t is equal to 1. Typically, it is done at the time equal to today. So for today, you assume whatever physical distances that you see, those are called comoving distances. And then if you want to know at any point of time early on in the universe or later on in the universe, what will be the physical distance between any of these fundamental observers, it turns out to be a of t times the comoving distance. Okay, so this is the concept of these fundamental observers. Okay, so now let's try to understand this symmetric three-dimensional metric, right? So dl square, the symmetric three-dimensional space that we are talking about, what kind of form you can have for this dl square. So let's try to understand. Okay. So for that, what we need to understand are these maximally symmetric space-like surfaces. Again, it is easier to imagine two-dimensional surfaces which are embedded in 3 dimensions rather than going directly to 3 dimensions. Okay, so let's look at some of the two-dimensional surfaces that we know which are symmetric, right? So for example, you can think about an infinite plane. This is something that you are completely used to, right? So let's start from there. So what is the length element on the infinite plane, right? So the length element on this infinite plane is just given by dx square plus dy square, right? So as simple as that, we have studied this. So you can think about taking this infinite plane and then generalizing it to three-dimensional space. You just get dx square plus dy square plus dz square. That's it, right? So nothing complicated. So this is the kind of arguments that I'm going to do in order to move us from two-dimensional symmetric spaces to then three-dimensional maximally symmetric spaces. Okay, so we considered the infinite plane. Can we think of anything else which is two-dimensional but which is also symmetric, which is homogeneous and isotropic? So one of the things that you can think of is the surface of a sphere, right? If you think about a surface of a sphere as a two-dimensional surface, and if you were a two-dimensional being on the surface of this sphere, then you will notice that, yeah, indeed, the surface of a sphere is homogeneous unless it is spinning or something, right? So it is homogeneous and isotropic. So if you are at this location, it is no different from a location here or a location here or a location here, right? There's no difference whatsoever. It's also isotropic. Whichever direction you look, it looks the same, right? So this is a maximally symmetric two-dimensional surface, right? So what is the line element, or how can we measure distances on this particular surface? Right? So let's try to think about it. So the way to do that is to write down the three-dimensional distance on this surface, which will be given by dl square is dx square plus dy square plus dz square. But remember that we are on a two-dimensional surface, right? So we have to obey some kind of constraint equation, which will make sure that we are lying on the surface of this sphere. Okay. So what is this constraint equation? So the constraint equation that we will have is capital R square is equal to x square plus y square plus z square. Okay. For the two-dimensional being which is living on the surface of the sphere, it cannot understand that there is a third dimension. But if there was a third dimension which has this kind of a metric, dl square is dx square plus dy square plus dz square, it can try to understand what is the metric on its own surface of the sphere, right? And so in order to do that, what you have to understand is this constraint equation, which is r square is equal to x square plus y square plus z square, and then try to remove this dz or try to express this dz in terms of x's and y's. Okay, so that is something that you can do by using the constraint equation. Okay, it turns out that it is better instead of working in these xy coordinates, it is better to work in the theta phi coordinates, which will define any location on the surface of this sphere. Okay, so what you do is you define z is equal to r cos theta, right? X is equal to r sine theta times cos phi, and y is equal to r sine theta times sine phi, right? So when you do these kind of definitions, you automatically guarantee that this constraint equation is satisfied. Okay, and once you do that, then you can express what is dl square in terms of d theta square and d phi square. This is exactly what you do. Okay, so this is the metric element on the surface of a sphere given in the units of or in terms of the coordinates theta and phi. Right? So this is describing not a plane surface, an infinitely long plane, but now a curved two-dimensional surface, which is nevertheless homogeneous and isotropic. Right? So the reason to give you all this background is now that we want to transfer ourselves to three-dimensional spaces, which are again homogeneous and isotropic. Right? So these maximally symmetric three-dimensional metrics, that's what we want to talk about, right? So now we can generalize the initial two-dimensional plane, infinite plane that we talked about. We go to 3 dimensions, then it becomes dl square is dx square plus dy square plus dz square. Okay. Then there is the thing which is about the curved surface, right? Think like we are some sort of three-dimensional beings who can only perceive things in 3 dimensions, right? But somehow our three-dimensional surface itself is positively curved, just like the curved surface of the sphere that you saw previously, right? So this is something that you can imagine just because you can perceive things in 3 dimensions, right? So it is easier for you to imagine a curved surface, a curved 2D surface, because you can visualize in 3 dimensions. But maybe we are not able to visualize it, but we can still write down the mathematics for it, right? So this is how you can write down the mathematics for it, right? So this is the generalization in 3 dimensions, where now this dl square we are expressing as dx square plus dy square plus dz square plus some other coordinate dw square, which we are not aware of, right? But who says that this should just be plus, right? It could also be minus, and still it obeys these principles of homogeneity and isotropy, because we are not doing anything in terms of the x, y, z coordinates. So your space-time, your metric element on this 3-dimensional space could also be of this third form, dx square plus dy square plus dz square minus dw square, right? So it could be this form or this form or this form, right? There are these 3 different possibilities that we have. And of course, we are introducing a 4th coordinate, but what we have to think about is this 4th coordinate. We need to specify some sort of a constraint equation so that you lie only on the 3-dimensional subspace of this 4-dimensional space, right? And so the constraint equation, just like we wrote down in the case of the surface of a sphere, it will be something like this, where r square is equal to x square plus y square plus z square plus w square. So this will allow you to trade off the w and then work out what the metric is in the 3-dimensional subspace. Similarly, for the last case, the 4D space with a constraint equation, what you can do is you can think about a minus r square is equal to x square plus y square plus z square minus w square. So this r, capital R, is a special quantity, right? So this is the radius of curvature that you have, right, for your space, okay? And so based on this radius of curvature, then you are able to then get rid of this particular W coordinate. Okay, so that's what we are going to do. Now, as I told you, it is much simpler if you work in these kind of spherically symmetric coordinate system, right? So in that case, in the sphere case, we had r theta phi, but here, or theta and phi in that case, now we need one more coordinate. So the extra coordinate that we are going to use is going to be chi, theta, and phi. Okay. So if you express now, if you take this dx square plus dy square plus dz square, and again express this x, y, and z in terms of chi, theta, and phi, then what you get is the metric for, say, flat space. When you consider the first equation, you get a metric for a positively curved space, which is shown in the middle equation, and an equation for a negatively curved space, which is shown at the bottom, right? So these are the maximally symmetric 3-dimensional metrics that you can get, okay, which are nevertheless homogeneous and isotropic, but still can be put in the initial equation that we saw for the full metric, for the full 4-dimensional metric that we have. Okay, so this is what is given just based on the assumptions of homogeneity and isotropy, and the fact that the universe does change in time, and we can have these foliations which are maximally symmetric for the 3-dimensional spaces, but then there is something that can change with time that allows a change in time. Okay. So that brings us to this particular Friedman-Robertson-Walker metric, which I've derived from heuristic arguments. You can derive it more rigorously, and which was done more rigorously by these gentlemen. Okay, so what you get are these Friedman-Robertson-Walker metrics. The metric for the universe, which is homogeneous and isotropic, it has to be of this form: ds square is minus c square dt square plus a square of t times a d chi square plus some quantity f square of chi, which goes in front of d theta square plus sine square theta d phi square. So this is something that you're used to, but then we are putting a f square chi in front of it. So this is the angular distances. We are putting a f square chi in front of it, and then there is a d chi square, right? So if you just look at it, the metric, the three-dimensional metric that you're used to in Euclidean space, it is nothing but d chi-square plus chi-square times d theta square plus chi-square sine square theta times d phi square. So this is something that you're completely used to, right? When you go to positive curvature, negative curvature, what happens is this chi-square, it turns into a slightly different function which depends upon the curvature of the universe, right? If it has a positive curvature, it looks something like this. If it has a negative curvature, it looks something like this. If it is flat, then it's the same thing that you're used to. It just becomes chi, which means the f square chi here will become a chi-square. That's it. Okay. So the quantity in the square brackets is something that you're used to, slightly generalized now for cases of positive and negative curvature. But what you're getting in front of this metric, this three-dimensional submetric, is a square of t, which allows the space to expand or contract. We don't know, right? A priori, we cannot say. It's just that there is a function of time which goes in front of it. That's it. And then there's this minus c squared dt squared that we have put in. Okay. So no equations of general relativity used yet at all. Only homogeneity and isotropy. That's it, right? Okay. So given this, now let's try to understand how we can understand the velocities that galaxies may have given this particular metric, given this particular form. So imagine that some of your galaxies, right? Imagine two galaxies. One is our own galaxy, and the second one is some other galaxy which lies far away. Okay. Now this galaxy and us, we have some distance between us, right? Let's call it r physical. That's the physical distance between us and that galaxy. We want to know what is the velocity of this galaxy, how we will see this galaxy moving away from us, right? Or moving towards us, whichever direction, doesn't matter, right? So if you look at the velocity, it is nothing but the derivative of the physical distance with respect to time. And remember, the physical distance is nothing but the comoving distance times the scale factor, right? And the scale factor a of t, it can change with time, right? So we are trying to understand what is the derivative of a of t times the comoving distance, okay? And we are going to try to take a derivative of this particular quantity now, right? So when you take a derivative of this quantity, what you see is that you're going to apply a chain rule, right? Because this is a derivative of the product. So we'll apply the chain rule. So you get dA by dt times r co-moving plus a of t times dr co-moving by dt, right? So you get these two terms for this equation. So this dA by dt, you can write it down as a dot, right? So this is a dot. And then you divide by a, you multiply by a to the numerator and the denominator. So the denominator is just here. But a times r co-moving is nothing but r physical. Okay. So you get a dot by a multiplied by r physical. That's the first term that you get. The second term that you get is a of t times dr co-moving by dt, right? And so this is the second term that you get, right? Now imagine if these two galaxies that we have, if they were fundamental observers, which means that their positions on these co-moving coordinates doesn't change. If that is the case, then this term will go to zero, the second term will go to zero, and all you will be left with is the cosmological recession velocity that you have here, okay? So something that comes about just because the scale factor changes with time, right? So this particular part, right, a dot over a times r physical, this is called a cosmological recession velocity. But your galaxies may not be fundamental observers. They may be moving a little bit here and there. If that is the case, then there is also this peculiar velocity term, okay? As you go further and further and further away, these peculiar velocities are not too large. They are of the order of 200 kilometers per second or so. So this term starts to dominate, on cosmological scales, it is this particular term which starts to dominate. And so that is exactly what you have learned in your A&A class, right? So the astronomy and astrophysics introductory class, which is the velocity is given by some term A dot over A times the physical distance between galaxies, okay? So this A dot over A is nothing but the Hubble constant today, or a Hubble-Lemaître constant today, okay? So then you can imagine this as velocity is h naught times the distance, right? Okay, so this is basically what the Hubble's law was, okay? This particular constant, A dot over A, we have learned to measure these constants. The value that is basically known today, the order of magnitude for this value is of the order of 70 kilometers per second per megaparsec. This is known to an accuracy of a few percent. There are still some discrepancies between different groups, but this is the order of magnitude, right, that we get for the Hubble constant. So all these galaxies that we see, they are receding away from us. A dot over A, the sign of this A dot over A is actually positive. And that's what we can understand, we can try to understand from the initial metric that we started with, okay? So at this point, I would take a pause and I would like to answer some of the questions that we are getting, okay? So I see there are a few hands which were raised, but then there is also a message in the chat box, okay? So let me first take the message in the chat box, and people who have raised their hands, it would be best if you can also write down the message in the chat box, okay? It becomes easier. So let's take the first question. So this is about, it is difficult to imagine. So could you explain a little bit more about negative curvature? Indeed, so it is quite difficult to imagine what negative curvature will look like, right? But let me give you an example of a two-dimensional surface which has a negative curvature, okay? So have you seen the surface which describes the saddle on a horse? Right, on the horse's back, right? So let me just quickly go to sharing my screen on the iPad so that I can maybe draw it. Okay. Let's see, start share. So I hope you can see my screen right now. So the surface of a saddle on top of a horse, right? It looks something like this. Right? Maybe I should draw another thing here, another thing here, right? So my hand is shaking a little bit. So let's suppose you are sitting on top of the saddle at this location here, right? What negative curvature means is that you have a curvature which is going in one direction here. So you are kind of at a minima at this location, and then you are at a maxima if you look at the perpendicular location at a different on a different side. Okay, so this particular surface is an example of a two-dimensional surface which has a negative curvature. A three-dimensional surface with a negative curvature, especially which is constant everywhere, that is something which is difficult to imagine, but we can nevertheless write down the equations. Okay, so I hope that helps in answering that particular question. Okay, so let's see. There are quite a few more questions. So some of them are being directly sent to me. Some of them are sent to everyone. So that is perfectly fine. So let's see. Is Maximally... Right, so in maximally symmetric 3D metrics is this plus W square minus W square. They stand for these positive and negative Kerr spaces. Yes, that is indeed the case. How do we decide which one is positively Kerred and which one is negatively Kerred? Is it our own assumption, etc., etc.? So this is an interesting question. In fact, even to figure out whether our space is positively Kerred or negatively Kerred, it's a very, very difficult task. Okay, so imagine you are sitting on top of this saddle or even on the Earth, right? If you try to draw triangles on the Earth, in the neighborhood, everything just looks flat, right? Because the curvature of the Earth is so big that if you draw small triangles, it is basically similar to Euclidean geometry. But now if you start to draw bigger and bigger and bigger triangles, then you will start to see that the theorems that you learn in geometry, they don't apply anymore, okay? So for example, one of the theorems that we learn in geometry, in this Euclidean geometry, is that the sum of the angles of a triangle is about 180 degrees, right? Is 180 degrees, sorry, not about, is 180 degrees, right? So if you now draw bigger and bigger triangles where the sizes of these triangles are roughly or of the same order of magnitude as the curvature of the space that you're in, you start to see problems. You don't see that it is 180 degrees. You will start to see that it is either bigger or smaller than 180 degrees. And that actually can help you decide whether you are in a positively curved universe or a negatively curved universe, okay? Again, it is also difficult to understand these things because the curvature that is happening, right, that is not in one direction as such, right? This curvature is happening in some this fourth direction, right? And so it's not like you can travel in one direction and you will recognize a negative curvature for the three-dimensional space. Remember, it is still isotropic, right? So you cannot single out any direction. So that's the reason why it is a little bit complicated to imagine. And the only thing that you can do is to actually think about it in terms of these equations. Okay. Right. So what do you physically mean by comoving? So comoving is nothing but, so I told you that there are these coordinates, right? And in terms of this, so you establish some kind of coordinate system. And then all that is happening is that everything is just expanding as a function of time, right? Or contracting as a function of time, right? It's just changing in terms of a scale factor. So all you are doing is you're saying it will be very difficult to write down equations if I try to figure out or try to write it down in terms of the physical distances, because these physical distances keep on changing as the scale factor changes. So let me take out this expansion that is just happening because of the scale factor and define new coordinates. So all that is happening in comoving coordinates is that you are taking out this expansion so that the equations then become simple. That's all. Okay. So comoving coordinates is nothing but that. Okay. Why do we divide and multiply in the slide expansion of the universe? Why do we divide and... Okay, I'm not entirely sure what this question is supposed to mean. So, so there are quite a few questions now. So I suppose that you can try to put in some more of these questions on a slide or on the Google Doc, so then that I can answer these questions. Okay. There's one question maybe that I will take. So this is like, what is the assumption behind assuming the cosmological principle? So, I mean, the main assumption is that the universe is homogeneous and isotropic. What you can ask is, can we test these assumptions? And the answer to this is yes, we can test these assumptions. You may have heard about something called a cosmic microwave background. We will come to it in the next set of lectures. So there I will show you explicit proof that shows that yes, indeed, the universe is to a large degree isotropic. Okay. And for homogeneity, we have actually mapped out all these galaxies. We can try to do number counts as a function of larger and larger and larger and larger spheres. And they actually tell us that the universe is homogeneous. Okay. So these assumptions that we made, they have some basis in observations as well. Is it perfectly homogeneous and isotropic? Of course not, right? We see that each direction is different. Somewhere you see Jupiter, some other place you see some other star and so on, right? So it's a matter of how big scales you average over. So when you average over larger and larger scales, you do see that we do indeed see this homogeneous and the universe to be homogeneous and isotropic. Okay? Okay, so let's move on to the next set of slides. So I will stop the broadcasting from the iPad. I will go back to sharing my screen. And I will try to come to, let's see how much time. I still have 10 minutes. So maybe I'll go to this particular slide. Are you able to see my screen? I suppose you are able to see my screen. Let me check on the iPad. Yes, you are able to see my screen. Okay, so You have learned this in the ANA course, so I will just go very quickly to it. So this velocity distance relation, right, is something that you can actually observe in the neighboring universe. This is what Hubble did using velocity measurements from Slipher and his own distance measurements using something called Cepheid variables. I suppose you have learned a little bit about this in the ANA course. So what you're seeing is this plot of distance on the x-axis, velocity of galaxies on the y-axis. He had gone out only up to like 2 megaparsecs or so something like 6 million light years roughly. Okay, and he drew a straight line through it. I mean, people are brave in order to. He was quite brave in order to draw a straight line through it. But this is what he got, right? That indeed the galaxies that you can measure the velocities for and the distances for, they tend to show that the velocities are not just distributed like some positive, some negative. Most of them are positive, and the farther away you go, they become more and more and more positive. Okay, so this is something that was found by Hubble, and this is what, when you put it together with the assumption of homogeneity and isotropy and the kind of mathematics that I showed you, which showed you how to relate the scale factor and the changes of the scale factor to the velocities and distances, that tells you that the sign of this A dot is actually positive, at least currently in the universe. And if the sign of A dot is positive, then it means that the universe is expanding. Okay, so this was one of the observations which actually led Einstein to abandon his ideas of trying to build models for a static universe, for example. Okay, so there are theories, right? Nobody would have thought that A of t there, which comes in the Friedman-Robertson-Walker metric, is not a constant, right? It could have been a constant, could have been something which goes down with time, it could have been something which goes up with time, right? So the only way you can figure that out, theory cannot tell you that. You have to do observations in order to do it, right? And then once you have the observations, before you have the observations, theorists will have their own prejudices about what kind of models they would like to build, right? Like Einstein had, he wanted to build a static universe, right? But as soon as observations come to you, sometimes the theorists have to abandon these ideas, right? And that's why observations are so powerful, right? They can shape the directions of theoretical research as well, right? And to let people, even brilliant people like Einstein, they have to modify their concepts as newer and newer observations come, right? Okay, so Edwin Hubble is like a giant in cosmology, right? Even before he did this exercise, he had established that these galaxies that you are seeing, they are not some clouds of gas within our own galaxy, but they are actually extragalactic. They are much further away than the extent of our own galaxy, right? So he is considered one of the giants in astronomy and cosmology for these kind of contributions that he made. It was amazing, of course. You should read more on the Wikipedia page that I also listed. Okay. So now let's just try to understand what happens to photons in these expanding universe, right? So let's think about a galaxy which is further away, and then you are the observer. There is a photon which is released from this galaxy, and then it is going to reach you to the observer, right? So light, we know, travels on null geodesics, right? So ds square should be equal to 0. Let's assume that this light ray is moving radially towards us, right? And if it is moving radially towards us, everything is homogeneous and isotropic, right? So once something is pointing towards you, it will just keep on pointing towards you and reach you eventually, right? And so d theta and d phi, everything is 0, right? And so our metric, it simplifies to this very simple form, right? Minus c square dt square plus a square t chi square. Right? I have put in d theta equal to 0, d phi equal to 0. So this is what you get. So now let's try to use this equation and then integrate using some limits, right? So you have c dt is equal to a of t times d chi, right? So I divide by a of t downwards. Now, how do I define my coordinate system? So let's assume that this particular galaxy is at a coordinate chi, okay? And the observer is at a coordinate where chi is equal to 0. I could easily have switched them. It doesn't matter. Okay. So one is at 0, another one is at chi. Okay. So let's consider that a light ray or light was emitted. This is an electromagnetic wave, right? And so let's assume that this is one of the crests, right? So this is a crest and this is a trough. So at the crest, when this crest was emitted, the time was TE, so T emitted. And then when it was received, when this particular crest was received, the time was TR. Okay, and so I'm going to integrate this quantity from T emission to TR. Okay, on the right hand side, I will have an integral. So T emission is done at a coordinate chi, so that chi is here. And then the T receiving is at coordinate 0, so the 0 is here. But since I have done a flipping of the integral limits, I have put in a minus sign here. That's all. Nothing complicated, right? In fact, none of the right-hand side will matter, as you will see soon. Okay, in terms of what I'm trying to say. Okay, so now we have tried to understand this crest in this particular electromagnetic wave, when it was emitted and when it was received. We have tried to write down this particular equation for that. Similarly, what you can do is you can take the next crest that comes, right? So that was emitted at a time TE plus delta TE, where C times delta TE is nothing but the wavelength of the light, right? Okay, so this was emitted at TE plus delta TE, so it will be received at TR plus delta TR. We don't know what is the relationship between delta TR and delta TE. That's what we are trying to figure out, okay? But we know that it will be received at TR plus some delta TR, right? So let's just write down that equation. Sorry, this is a typo. It should be delta TE. So TE plus delta TE to TR plus delta TR, C dt by A of t, is nothing but again minus of integral from 0 to chi d chi, right? So now this is pretty simple. So now what we are going to do is we are going to do a subtraction of these two equations. So when you subtract, the right-hand side will exactly cancel out because these things have stayed at their same co-moving positions. So it doesn't matter. So this cancels out completely. What you are left with are equating these two, you have to subtract these two quantities, but because the right-hand side has subtracted out to 0, these two quantities here, they should be exactly equal. Okay. So when you do the subtraction, what you're left with is an integral over TR to TR plus delta TR and TE to TE plus delta TE. This is a small interval. Imagine when the light waves are emitted, right? The time between these successive crests are extremely small, right? So there you can assume that A of t has not changed much when the first crest was emitted and the second crest was emitted, and A of t has not changed much when it was received, right? So doing those approximations, you are left with this particular equation, okay? That C delta T over A of t is equal to C delta TR divided by A of TR, okay? Now C delta T is nothing but the lambda emission, right? As I told you, C multiplied by the time interval between these two excuse me, is nothing but the lambda emission, and this is nothing but lambda received, right? What is the wavelength of light which is received? And so now you can see that I can relate the wavelength of light which was received to the wavelength of light which was emitted at the location of this galaxy in an expanding universe, or in a universe which has a scale factor which changes with time. Right? It doesn't have to be necessarily expanding, it can be contracting as well. In any of these cases, C delta TE by A of TE should be equal to C delta TR divided by A of TE. Right? So let's write it down in terms of a lambda. So lambda R, which is lambda received, this divided by lambda emitted, is equal to 1 plus Z, which is a definition of my redshift now, redshift of the line. And this is given by A of TR divided by A of T. Okay, so when the light was received divided by when the light was emitted, that is what will define what are the ratios of the wavelengths of light. Okay, Now you can imagine how this will be able to help you, right? So if you have a galaxy, it emits some light at some rest frame wavelength, right? So there are all these lines in the light which is coming from this galaxy. If you can measure the wavelengths of these lines, you can identify what is the identity of these lines. You can figure out what was the scale factor at the time this photon was emitted from that galaxy. This is pretty cool, right? You can just use the wavelength of light that you see today in order to figure out what was the scale factor, how the scale factor of the universe has changed when the galaxy was at that location, right? Or when the photon was emitted from that galaxy, right? Remember, there is a certain amount of time that has passed by the time that photon came from that galaxy to us, and in between the universe has expanded or contracted, right, changed in terms of its scale factor, and that's why the wavelength of the photons also changes. So this is the redshifting of photons that happens in a changing universe. Okay, so this is the last slide for today, and then I'll move to questions. So what you can do is you can define distances in the universe in an expanding or contracting universe, in a universe which has this kind of scale factors. Okay, and so there are two ways to define distances, and in real life, you are used to measuring distances in a very absolute manner, right? That there are no two different distances. But once you have these scale factors which are changing the physical distances between objects, then you have to worry about it. Okay. So one way that you can define the distances is via something called angular distances. And so what this does is it relates the angles that any object subtends to its physical size. Okay, or you can think about what is the solid angle that is subtended by a particular physical area of an object which is further away from you, right? You can define a distance accordingly, right? So for example, if I have this iPad pencil, if I know what its length is, and if I put it at a different distance, I can measure the angle at the end points of this pencil and figure out what the distance to this pencil is, right? So that distance, if you can measure distances in this way in a universe which has these scale factors and so on, it's called angular distances. So this is given by d angle is equal to the physical area divided by the solid angle that is subtended, or it's the length divided by the angle, the angle that you're used to that is subtended by the endpoints of this ruler, right? So this, you can look at the metric and you can convince yourself that this is nothing but 4 pi times f square chi times a square of d divided by 4 pi. Okay? All you have to do is think about a sphere and the surface area of this sphere. The surface area of this sphere will be nothing but 4 pi times f square chi times a square of d. And then the solid angle which is subtended by this sphere is 4 pi. And so you take a ratio of this, take it to a factor half, and you will see that these angular diameter distances, when you measure them, they turn out to be f of chi divided by 1 plus z, or 1 plus the redshift of this object that you are considering, right? So it's not simply the coordinate distance to that galaxy. Angular diameter distances are not simply the coordinate distance to your galaxy, but they get modified with this factor 1 plus z. That's the first thing. The second thing is there is a f of chi here, which means you can learn about the geometry of the universe if you can actually measure these angular diameter distances as a function of redshift. Again, a pretty cool and amazing thing, right? You measure these angular diameter distances, you can learn something about the geometry of the universe too. This is in fact how we know what is the geometry of our universe. Okay, this is what allows you to draw like bigger and bigger triangles, right? Think about when you're measuring any of these angular diameter distances, you're actually drawing triangles, right? So there's something for which you know the physical size, and then you know the angle toward it. So you're drawing a big triangle, and the geometry of this triangle will help you to understand what the geometry of the three-dimensional of this homogeneous and isotropic spaces on large scale. Okay. Similarly, you can also define something called a luminosity distance. If I have a bulb which has a known luminosity, I can put it further and further away. I can measure what is the flux that is received at my location, right? And I can define a quantity called the luminosity distance by taking these ratios of the bolometric luminosity. So luminosity, so the energy integrated over all wavelengths per unit time, right? So that's the bolometric luminosity divided by 4 pi times the flux that you received at your location. If you use that quantity, if you use this ratio, then you can define something called a luminosity distance. The further away you put things, the dimmer they will be, right? It's as simple as that. That's what is expressed by this equation. But then you can do all these kind of number counting of photons. Remember, there's an energy expression here. So the energy received, you have to think about the fact that the photons, they will also be undergoing a change because of the scale factor and so on. So if you do all these, you write down all these equations, then what you get is that the luminosity distance is given by f of chi, now this time multiplied by 1 plus z rather than divided, right? So you can measure these angular diameter distances, luminosity distances, you can figure out what the geometry of the universe is, okay? So, so I think this may be a good place to stop. This is already 12:30, so I will take some questions now, okay? So one of the questions that I saw immediately which came up, which is what is this f of chi exactly, right? And so I will have to go back to my slides in order to show you what is f of chi. So f of chi is nothing but one of these functions, right? So f of chi, if you are living in a flat universe, it is something that you're completely used to. It's the same as the distance, chi, okay? But if you're living in a positive curvature universe, then it is some constant r, which expresses the curvature of the universe, multiplied by the sine of chi divided by r. Okay, that's what this function f of chi is. If you are living in a negative curvature universe, then it is r times sine hyperbolic of chi by r. Okay, so that's what this function f of chi is. Okay, so even if you're living in a flat universe, right? So that's another thing that maybe I should stress. Even if you're living in a flat universe, which has a scale factor which changes with time, the luminosity and the angular diameter distances are not the same. Okay, they are different by these factors of 1 plus z squared. Okay, luminosity distance is larger than the angular diameter distance by a factor of 1 plus z squared. Okay, even in a flat universe that you're used to. This happens just because of the scale factor. Okay, okay, good. Is there any difference between the physical distance and the angular diameter distance? Yes, so there is a difference between the physical distance and the angular diameter distance. The physical distance today that you see is nothing but the scale factor multiplied by the co-moving distance that is there today. Okay, if you just do this, right, in suppose a flat space, then it works out to be true. But if you do this in a positive curvature or negative curvature, right, where you then call this chi as it depends upon what you call the co-moving distance. If you call f of chi the co-moving distance, then yes, indeed, a of t times f of chi will be the angular diameter distance. So then that's not a problem. If you call chi the co-moving distance, then it is a more complicated function, which is a of t times f of chi. Okay. Okay. Any other questions? Let's see. Physical distances are in 3 dimensions. Yes, the physical distances that we are measuring are in 3 dimensions. That's right. Okay, so I can maybe also allow, I can allow a few hands to be, those people who have raised their hands to ask some questions. So maybe Shari Kapoor, can you please unmute yourself and maybe ask your question?
Hello, am I audible?
Yeah, I can hear you.
Good afternoon, sir. So my question is, what is the physical significance of cosmological recession velocity and the peculiar velocity? And as the universe is expanding, how do they contribute to it, or how do they change accordingly?
Right. Yeah. So that's an excellent question, and you will learn a little bit about structure formation in some of the courses which will come up. Okay. And so you will see there that these velocities that you see, these peculiar velocities, how they change and how they contribute. And you will see that the cosmological recession velocity is what starts to dominate. Okay, as you go further and further along. I will give you what are the typical values of these velocities. These are of the order of 200, 300 kilometers per second. So the how much these galaxies can move with respect to some fundamental coordinate, right? That is not a lot, okay? And that is of the order of these 200, 300 kilometers per second. Okay. In order to figure these things out, right, figure these kind of things out, one of the things that you can do is, for example, consider objects which are at the same redshift roughly, right? And so their co-moving distances are roughly the same. And so the cosmological velocities, they almost cancel out, right? And so then you can figure out what is the dispersion of these velocities, the remaining velocities, and you find out that it's of the order of 200, 300 kilometers per second. Okay. For example, if you go to a cluster, a galaxy cluster, there the velocity dispersions are actually the highest because their peculiar velocities are driven by the gravitational potential of the cluster itself, which has like 10 to the 15 solar masses or so. So there you see like 500, 600, 700 kilometers per second. But in like if you take like average velocities of galaxies on larger and larger scales that you see, they are not of a huge order. They will be of the order of these 200 kilometers per second or so. So you can use, for example, the 70 kilometers per second per megaparsec Hubble constant that I told you. And you can ask, okay, at what distances peculiar velocities will be of the order of, say, 1% or 5% of the recession velocities. And you can figure out what these distances are. Okay. Maybe I should leave it to you as an exercise. Okay.
Thank you, sir. So now will we get to know about the physical significance too?
Physical significance, right? So the physical significance here is that the change in the scale factor that causes a particular coherent velocity that is present to all galaxies which are a certain distance away from us. Okay, that's the physical meaning of this cosmological velocity, because it's a coherent velocity. All galaxies which are in this direction, in that direction, in third direction, whichever direction, but at a certain distance away, they all have the same velocity. That's why it's called a cosmological velocity, because it's shared by all the galaxies which are at a certain distance away from us. Okay, if you go and sit on that galaxy, you will see the same exact thing. Some other galaxies which will be at the same distance away from that galaxy, observers on that location will see exactly the same thing. Okay? So that's the reason why it's called a cosmological velocity. Peculiar velocities can be different because it depends upon your place in the universe, right? With respect to you, how these fundamental or the galaxies are moving with respect to the fundamental coordinates, that gives you rise to the peculiar velocity. So these peculiar velocities are dependent upon the location and directions and so on and so forth. Cosmological velocities there. So I hope that helps.
Thank you, sir.
Yeah, thanks. Okay, so let's go to the next question. Shreya, do you want to unmute yourself?
Good afternoon, sir.
Yeah, hi.
Sir, in the Redshift slide, there is an integral expansion where the c squared delta TE minus upon AT that becomes 0. So how does it become 0? So the right part of the equation, that integral d chi. So
sorry. So light travels on null geodesics, right, where ds square is equal to 0. And so what I've done is I've just taken this equation. 0 is equal to minus c square d square plus a square of t times d chi square. And then I just move the c square dt square to the other side. Okay. So I'm not equating this equal to 0, this equal to 0. No, I'm saying that because ds square is equal to 0, c dt should be equal to a of t times d chi.
Sir, what is this ds square as a physical part of the equation? Physically?
No, so ds square is this. Is c square times this proper time, right? And for light, you have this ds square, which is equal to 0, right? It travels on this null geodesics where is the distance in space time.
Okay, sir.
Right?
Oh.
Yeah. Okay. So maybe the next question, Junik, do you want to unmute yourself?
Hello, sir. Am I audible?
Yeah, I can hear you.
Okay. Thank you, sir. This lecture was really beautiful. Sir, my question was from the expansion of the universe equation, the peculiar velocity function. How does dark energy affects this expansion rate? Does it changes the peculiar velocity function? Because the first part of the equation that remains constant all over the surface, or almost everywhere. So my question is, how does dark energy affect this?
Yeah. So I would suggest you to wait for the next set of lectures. What we are going to do next, so until now, all we have done is homogeneity and isotropy, that's it, right? And work out what the metric is, and we got quite a few things out of it, right? Next lecture, what we are going to do is to understand how to calculate the scale factor as a function of time, right? Because that is an unknown. Right? And that will depend upon the constituents of the universe. How the scale factor changes as a function of time will depend upon these constituents. And so we will do it tomorrow. And I will try to give you a Newtonian derivation of it, also the GR derivations. I will at least skim through it or tell you how they work, etc. So just wait for some time. You will get the answers to it.
Okay.
So now it's almost 12:45. So what I'm going to do is I'm going to stop here so that you can grab onto the lunches and then get ready for the next set of lectures. What I encourage you to do is to write down your questions which have not been answered in the Google Doc. I will take a look at it and I will answer a few of those. And I would like to ask you to please restrict your questions to the material that was taught today, so that it becomes easier for me to address them. Okay, and then it also becomes easier for everyone to follow. Okay. Okay. Thank you so much for today. I will see you tomorrow.